Hello everyone, my name is Zhang, coming from Fudan University. It's a great honor to present our paper, TextExerciser, Feedback-Driven Text Input Exercising for Android Applications. This paper is a joint work from Fudan University, Johns Hopkins University, University of Texas at Dallas, and Tsinghua University. Dynamic analysis of Android apps is often used together with an exerciser to increase its code coverage. One big obstacle comes from the text-based inputs, which are often constrained by the nature of the input field, such as the length and character restrictions. Furthermore, these inputs often require a non-trivial constraint that is hard to be satisfied during analysis. For example, a personal profile description field of an Android app may require text that at least 20 characters and do not contain any special characters. Such constraints for text inputs are very popular in Android apps. Thus, the key problem for exercising Android apps is how to generate valid text inputs. Due to the difficulties of generating text inputs in existing Android apps, some researchers propose to adopt either a heuristic approach or predefined formation. For example, summarize the input patterns to predefined inputs, or use machine learning to automatically learn inputs. Besides, several other tools use predefined third-party login, such as Facebook or Google login, to circumvent text input UI, such as login page. However, these input patterns are diversified, and different apps have many ways to constrain text inputs, which either do not support third-party login or require unique input constraints that are different from general heuristic rules. Furthermore, these text fields are often correlated. For example, the value of a maximum wage field should be larger than the one of a minimum wage. Therefore, existing works such as rule or learning-based summarization of text input patterns often fail to satisfy using constraints. But a single failure will stop the entire exercising of the target app. Thus, we propose TextExerciser, an iterative feedback-driven text input exerciser which generates inputs for text fields of Android apps. The key insight here is that if a text input does not satisfy the enforced constraints, the Android app, either the client-side program or the server-side validation, will provide clues or hints for the malformed input, which can be used as a feedback for improvement. The main contributions of our work are summarized as these three aspects. First, we propose the first feedback-driven input exerciser that generates text input using a constraint solver based on the hints from the target app. Second, we implement a prototype of our text input exerciser and open source it on GitHub. Third, we evaluate the performance of TextExerciser on popular Google Play apps. The evaluation results show that TextExerciser achieves higher code coverage than state-of-the-art tools and also finds more privacy leaks and vulnerabilities when combined with existing dynamic analysis tools. TextExerciser tries to understand hints shown on UIs of Android apps, and then extracts corresponding constraints. The exercising has three phases, as shown in this figure. First, TextExerciser extracts all the hints from app's UI with the hint extractor. Second, TextExerciser passes all the extracted hints and recognizes their semantic meanings. Lastly, TextExerciser generates a concrete input by feeding constraints into a solver, for example, these three. Then, TextExerciser solves the problem with generating inputs back to a touched Android app and extracts feedbacks, such as success or not hint. In the case of a not hint, TextExerciser will iterate in the entire procedure until TextExerciser finds a valid input. The first phase of TextExerciser is to extract hints, which are related to text inputs from an Android app. There are two steps in this phase: identify hints from app UI and map hints to the corresponding input fields. There are two types of available hints in Android apps: dynamic hints and static hints. A dynamic hint appears once a user inputs an incorrect text into the Android app. For example, the app may alert the user that a specific password must not be shorter than 6 characters. As a comparison, a static hint appears together with the text input field. TextExerciser extracts dynamic hints via differential analysis that compares wedges before and after inputting a text input into the app. Information that appears in the widget after text input is considered as an hint. However, for identifying static hints, we should first separate them from other non-hint texts. Thus, we train a hint classifier. The positive training samples come from dynamic hints extracted from those Android apps via differential analysis, and the negative samples come from information extracted from app windows without any text input. Next, TextExerciser needs to map extracted hints to corresponding input fields. TextExerciser adopts two methods in the mapping. First, TextExerciser maps keywords extracted from hint to the text related to the input field. For example, the same keyword, gamer ID. Second, TextExerciser adopts a shortest distance method to find the closest input field and map each hint to its nearest input fields. After extracting hints from Android apps, TextExerciser uses hint parser to parse the semantic meaning of these hints. The goal here is to extract constraints which can be understood by computers from those hints which are written by human language. The high-level idea of understanding these hints is based on an observation that these hints with similar semantics often have a similar syntax structure, and therefore, TextExerciser can cluster these hints based on their syntax structures, and then extract the constraints from the syntax structure. Thus, after manually labeling 1,200 popular apps, TextExerciser trained classifier which cluster these hints into 4 major, 10 minor, and 18 sub-minor categories as shown in this table. Then, for each hint, TextExerciser generates a syntax tree using the Stanford parser, and then traverses the syntax tree for constraint generation. At last, TextExerciser generates inputs that satisfy all the constraints converted from the extracted hints and feed them back to Android apps. Particularly, TextExerciser adopts this string solver, a popular solver, to generate inputs that satisfy all the constraints. Besides, app servers may send some text to Datasets through some external channels. for example, email and SMS. TextExerciser will pre-register several email accounts and phone numbers to receive such texts, such as PIN code. We evaluate the performance of TextExerciser on real-world Android apps via three main research questions. First, is TextExerciser more effective than existing tools in exercising Android apps? Second, can TextExerciser improve existing dynamic analysis of Android apps? Last, is TextExerciser efficient for generating text input for popular Android apps? All the apps in our datasets are coming from top 500 apps in each category from Google Play, except for game apps. The reason is that gaming apps commonly use figures to illustrate notifications, and most of their content are presented in the form of images. As aforementioned, we use 1,200 apps to train the model used in Haixin Parser. In evaluation, we use two sets of apps. The first one is a small set, which contains 40 apps. We instrumented these apps to compare code coverage with other related tools. The second dataset contains 6,000 apps, which is used to test the performance of the TextExerciser when exercising a large amount of Android apps. For answering the first research question, we combine TextExerciser with other UI exercisers, including the monkey, Zhibo, and Thought, because TextExerciser is a specialized text input exerciser, while others are general purpose. We replace the text input generator in each general purpose exerciser with TextExerciser, and compare the modified version with the original one for code coverage. The results show that both on the small and the large dataset, TextExerciser can achieve higher code coverage than state-of-the-art tools. Particularly, TextExerciser triggers 48.5% more activities and 29% more methods for monkey, 37% more activities, and 20.2% more methods for Thought, and 45.3% more activities, and 26.4% more methods for Zhibo. For answering the second research question, we combine TextExerciser with existing dynamic analysis tools. Particularly, we combine TextExerciser with Tendroid and Recon for detecting privacy leakage on the 40 apps. As a result, after manual verification of the true positives and false positives, we find that TextExerciser can help Tendroid and Recon find more privacy leakage. In this slide, we present the apps with additional privacy leaks found by Tendroid and Recon with the help of TextExerciser. They either use insecure configuration of SSL communication or transfer of user credential or private information in HTTP links. Besides, as a byproduct, TextExerciser also finds some bugs, for example, malformed text constraints or existing Android apps when generating text inputs. For answering the third research question, we evaluate the performance of TextExerciser on 6,000 apps. As a result, TextExerciser has an accuracy of 90.2% to identify hints from Android apps, and the hint parser can pass 97.3% hints and recognize their semantic meaning. Besides, In most cases, TextExerciser can generate a valid input in the first round. The number of trials is limited to 30, and only 1.2% of mutation will exceed its limitation. The major reason for these failed cases is that they require some specific external knowledge, for example, invalid code. In this paper, we propose TextExerciser, an iterative feedback-driven text input exercise, which generates text inputs for Android apps. Our evaluation shows that TextExerciser can achieve higher code coverage than existing tools with default text input generators. We also combine TextExerciser with existing dynamic analysis tools like TurnDroid and Recon, and show existing dynamic analysis tools are able to detect more malicious behaviors with TextExerciser than with existing exercisers. Thank you.